spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
Mic check.
Searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence. Waste of existence.
The sun is shining and the anxious earth is rising. I'm so happy.
We spend our life searching for the sense of belonging. Some people die before they fulfill their desires. Such a waste of existence.
What the heck is wrong with this thing? Oh, hey! Hi, Double Tribble here. Streaming from New Hampshire, live. Hi, my name is Ron, and I live in New Hampshire. And I live in a rural area of New Hampshire. I'm surrounded by all kinds of animals and forests and stuff. And I like to stream science and sci-fi, and sometimes I do IRL around here, where I, take pictures of animals or whatever is going on here. And today I'm going to try to do some science stream. But I didn't. I had a little technical difficulty before the thing started, so I'm a little bit late. I'm 17 minutes late getting started. So sorry about that. I actually had this thing planned for 1 o'clock, but put it back another hour to avoid a schedule conflict. But today, what I'd like to do is to build a buzzer or a bell, an electric bell, ding ding ding, that type of thing, like an alarm bell, something like that. And if you are watching on the VOD, I put my VODs on YouTube, so if you somehow stumbled upon this thing on YouTube and want to learn about electromagnets or bells or something like that, this is like a live stream So it will seem like it goes really, really slow compared to a typical YouTube video. And if you want, you can just go ahead and skip ahead. Or you can look at my, I might take this after I'm done with it, depends on how it goes. I might take it and trim it down and make it into a real video, for YouTube. And if I do that, I will post that on KXQE on YouTube. KXQE.com, or actually just KXQE on YouTube. So that's what I'm going to do. I didn't really plan this out too much. I just thought the reason why I did this, or the reason why I want to do this, I was watching a couple weeks ago, I was watching Tiny Toxic Tofu, who was also on Twitch. And she was doing stuff with buzzers, and she had all different buzzers she was playing with and stuff and hooking them up to batteries or power supplies or something. And I thought, oh, that would be fun to build a buzzer, to actually, build one from scratch on screen. Let me get my mic out of the way. Hang on just a second here. There we go. I said that would be a fun little project to do that, to build a buzzer on stream with just some scrap wire and stuff like that, and make a little electromagnet with a switch and stuff and have it and turn it into a buzzer. And as I was looking for stuff, down in the basement, just junk stuff to try to build it out of, I found a little bell here, or not a bell. It's this little thing here, which is this is actually a ladle. Imagine there was a handle on this thing. It was a steel or stainless steel ladle with a handle on it, and this little weld here, I don't know if you can see that too well, but it had a really bad weld, and the handle broke off years and years ago. And I was going to throw it away, and I thought, oh, this is kind of a cool little shape, this thing, I'll save it for something. And today's the day that I'm going to use it after all these years. And I found it. And I said, okay, in addition to doing a buzzer, I'll do a bell too. A little bell that rings. And so I found this thing. I said, that would make a nice little bell. I'll see if I can make that into a bell that will ring. It's full of stuff right now, but, have a little hammer that hits it and rings the bell, right? Electronically. And I also found this little thing, a little piece of spring steel down there. Everything's all rusted down there because it's just, that's where I'm in a humid area. So anything that is ferrous, which is what we're talking about today, right? Magnets and stuff like that, is going to be rusty. So a lot of these parts are rusty. But I found this little piece of spring steel, and I thought, okay, this would be great to use. And I did some experiments with it a couple days ago, and see, it's really springs. So I think that would be good for to try to build a buzzer or something out of. And I found some wire and a whole bunch of hardware down there. I've got this whole thing through little hardware and stuff like that I might be able to use. And what else do I have? I got some resistors. I have a resistor here. I tried to I was doing experiments with it, right? And I had an amp meter like this. This is an old amp meter that I found. And I had another one that was went up to 15 amps. And I hooked up. I was experimenting with this little coil here. I took this bolt and I wrapped wire around it to make a little electromagnet. Maybe you've done that before. You've seen people do that before or heard about that before. That you can make an electromagnet just by taking some wire and wrapping it around a bolt. Well, that's what I was doing. And I experimented with it. And I also have an old train power supply. This is from a train, with a little where you can control the train, right? Make the train go faster and slower, right? On a train tracks, those old type model trains, And I took this years ago and I put a fan in it, and I took took the output and hooked it up to a bridge here, a 4-way bridge and a cap, and turned it into DC instead of AC. It had an AC output on it for some reason. Anyway, so this thing is rated for about 1 point something amps, and I put all this stuff on it, and I can get about 4 amps continuous out of it now by doing that. So anyway, I hooked that up to this thing to see if I can make an electromagnet, and I also had an amp meter that went up to 15 amps. I said, okay, 4 amps here. I got an amp meter that's 15 amps. I should be good, right? But I didn't think. This is an inductor. When you hook stuff up to inductors, it stores the current, or it stores the energy in a magnetic field around the inductor. So when I hooked it up, the magnetic field grew on the thing and turned into a little electromagnet. Great, and I had my amp meter hooked up to it, and then when I disconnected it, pop, there goes my amp meter went. 15 amp meter went, even though I was only had 4 amps from my power supply. And the reason is because this thing, it spikes. It does it in a negative, and it was actually negative, right? In a negative amp spike when I disconnected it. That's the way inductors work. I was going to get into all the technical stuff about this, but Tiny Toxic Tofu is doing, and let me do a shout out to her here. I got a chat on this is for those of you watching on the VOD. This is a live stream on Twitch, and they have a facility here where we can type stuff in here. So let me see if I can get this. I'll do a shout out to her. Tiny Toxic Tofu. Let's see if that works. I don't know if she's got a. Let me see here. She's actually still on. She was on earlier today talking about electromagnetism. I think that'll work. I don't know if it's case sensitive or not. Let's see. All right. Yeah. Okay, that worked. Anyway, so she was on this morning talking about electromagnetism. She's been talking about electromagnetism for a couple weeks now. But and that's kind of what got me started on this. She was talking about buzzers a couple weeks ago, and that's what got me started in this whole process of saying, hey, that would be fun to build a buzzer, and now I'm going to try to build a bell, a buzzer and a bell. And maybe talk about magnets and stuff like that, because magnets are cool. magnets. When you're talking about electronics and physics, stuff like that, magnets are one of the coolest things in science generally. But anyway, so that's what I'm going to show you. I'm going to try to build it, and I got another meter. My other meter I popped. This one goes up to 300 amps, but I don't have the right shunt to put on this thing to do 300 amps. This shunt is only for, I don't know what it's for, 50 amps or 20, I don't know. But I hooked it up and it reads about 1/10 of it. So it's 30 amps. This will go up to 30 amps. So hopefully this one won't pop. And maybe we can adjust the circuit so that it doesn't do that anyway. So that it doesn't have that spike in it. I was reading about ways that you can do that. You can hook up a capacitor or a reverse bias a diode into the thing so that it reduces that current spike. It'll also make it spark less when it switches. So let me just talk about magnets for a little bit here. Right, here's some neodymium magnets. Neodymium is the current front runner on material for making magnets. You can make really powerful magnets that are really small with that material. You use iron and neodymium, and was it boron or something like that. And so you can make really strong magnets with it. And you probably know, right? Magnets have a north and a south. I broke this magnet right just yesterday. I broke this. They normally don't break. Ceramic magnets break all the time. If you have a ceramic magnet, it'll break really easily. But these neodymiums usually don't. But this one cracked. So the way they make these things, they make this out of, like I said, iron and neodymium and boron. But the thing is that it's really, I mean, it has iron in there, so if it gets exposed to air, it'll corrode, just like iron rusts, So that's the problem with this stuff. So they coat it with a coating, with a plating. And you can see this one here. You can see that it's in the inside. It's got that. It's a different color. The outside is just plated, to keep it from corroding. I'm going to check my sink here because I might be out of sync. I was doing some stuff there. Let me just check this really quick. I'll talk into the camera and then look at myself and see if it. No. All right, it seems to be in sync. Close enough, right? All right, so magnets have a north and a south. When they discovered magnets, they figured out that soon after they call them lodestones, natural magnets. It's just basically iron material that has become magnetized, usually from lightning, I guess they think, or maybe other processes. But but when they found magnets and they figured out how they worked and stuff like that, they discovered that they always pointed north, or they like to point north. And that's where compasses came from. This was hundreds of years ago. They figured this out, 1,000 years ago maybe. And so it turns out that only one end of the magnet turns to north, and magnets. So they have a north and a south. Let me see if I can pull this one off of here. These are really strong magnets. But so this one here. Sometimes they're set up so that like one end, this will be north and that'll be south or something. But this one's not set up this way. This one's set up so that the south is the top and the north is the bottom. See, I put a little S on it to know which one. That's south. I guess we'd flip it over this way. That's south. This is north. And if you take a you guys, this is probably all review for you guys, but in case you're not familiar with this stuff, if you put this is south on this magnet, and this is south on this magnet. When you try to push them together, you've done this as a kid, right? You try to push them together, they push away from each other. But if you put the north side to the south side, then it snaps right in. And they also found out that if you take a magnet and let it free float somehow, either hang it or put it in water or do something to make it free float, it'll turn and point towards north. The north end of the magnet will point towards the north pole of the globe. And by the way, they knew that the earth wasn't flat a long time ago, 1,000 years ago. They knew that. they knew that the earth was basically a sphere. And that it turns, and the top, and there's an axis that goes through it, and the top of the axis is the north, or from the way by convention we make the top north and the bottom south. And they found out that these things point towards the north. So you get a compass like this. Here's a compass that is for a boat, I guess. I got it at a garage sale a little while ago, and so. It's probably not. I've got all these magnets around here and stuff like that, so it's probably not working right. Yeah, it's not. It's pointing east. This is pretty close, actually. So what is that saying? That's saying that it's west? Yeah. So yeah, west is basically behind me. So it is working, But what happens is if you take these magnets, so I'll take the south end of the magnet and move it close to this thing and watch what happens to it as I move it close to it. See that? It just follows where the magnet goes. Now what it's doing is I'm putting the south end of the magnet here, and I'll move it up near the camera here, and you'll see that it's making a south. It's going towards the south. It wants the south. See this so the compass thinks that this is the South Pole as I move this around. See that? But if I flip it around and put the north, here's the north side of the magnet, and put that towards it, it goes completely the other way. And it wants to put its north towards the north magnet. So that's how compasses work. And the reason they point north towards the North Pole or near the North Pole is because the Earth is a magnet, basically. Inside the Earth is a there's a lot of iron in the middle of the Earth, and it's spinning, and it makes an electromagnet. is what the Earth does, because the inside is spinning, and it's right now it's the inside, the spinning of the axis on the inside is lined up with, so that the magnetic axis is more or less in line with the axis of the rotation of the Earth. But it isn't always like that. It can flip all different ways, and it floats a little bit. It's moving around over time, and they track that kind of thing. But the interesting thing is that the part of the magnet that points towards the North Pole, they called north end of the magnet, and the other side is south. But you think about it. The north, if I try to push this north towards a north magnet, it's gonna go the other way. The north end of a magnet actually is attracted to the south pole of another magnet. So actually, the Earth's magnetic south pole is at the north. You see why that works? Because a north pole of a magnet is attracted to the north pole, geological pole. But because the north pole of a magnet is attracted to that, that means that pole at the north, geographic north pole, is actually a magnetic south pole. So it's kind of confusing, but that's the way, right? It makes sense. That's the way it works. I should have went took some time and made some little graphics and stuff to get this, to make it sense. Let me do that. Let me draw that out right now. Yeah, if you're watching on the VOD, just feel free to fast forward to the part where I build this thing. Let me see if I get my little drawing tablet working here. I really get that in there. All right. Let's see if I can bring up my my drawing tablet. Oh, it's over here. There it is. All right. Move this over here. That over there. All right. All right, just take a second here. I try to find my. All right, there we go. All right, so I'm gonna do a little adjustment here, get this thing so you can see the whole tablet. that the whole tablet? Yeah, more or less. Right. A little bit smaller. All right. All right. Let me draw this because it's kind of confusing me just me talking about it. And I'll get to build. I'll build the thing a little bit later. As I said, if you're on the VOD, you're watching the VOD, feel free to fast forward to the part where I actually build the thing. All right. So here's the Earth, right? Let me make a. Earth is almost a circle, so get shapes, get a circle. Oops, no, that's not what I want to do. I don't know why that didn't work. All right, let me just draw a circle here. Jesus, all right, this is not gonna work too well here. All right, there we go. All right, there's the Earth. After it got hit by the asteroid 65 million years ago, it had a lump on the side of it. All right, can you see that? No, it's still not showing up, is it? There we go. All right, so this is the north of the Earth. North and south. So they found out that if wherever they were at, if they had a magnet and they let it float or held it on a string or whatever, it would point towards the north, no matter where they were, because the magnetic north or the magnetic pole right now is lined up with the axis of the spin of the Earth, or the rotation of the Earth. But the thing is, if I have a magnet, let me draw a little magnet here, and it's okay. So this is this is the compass pointing on a compass. You got a little compass here, and it wants to point up here towards the north. If this is a magnet, and this is the north end of the magnet here, then this up here has got to be the south end of the Earth's magnet, and this here would be the north end of the Earth's magnet. So if you think of the Earth as a big bar magnet like this, then this would be the south end of that big magnet, and this would be the north end of that big magnet. And that's why compasses point the north end of the magnet on a compass points up here to the south. It's the north geographic pole, the North Pole, but magnetically it's the magnetic south pole of the Earth. And the reason why it way down here it points up there is because you've got any magnet has these lines of force that go like this. The magnetic field that comes out of the magnet like this. And this one has one too, right? This one has one that goes like this. And it wants to line up with these lines of the magnetic field. Now I'm not going to get into a lot of the detail on it. If you want to get into detail, I highly recommend you check out Tiny Toxic Tofu and her stuff she's been doing. Oh, hi Ivan, how are you doing? Ivan Neo just joined us in chat. Let me give Ivan a shout out here. Let's see here if I can do that. So I'm a little rusty here on stream. It's been a few weeks since I streamed. All right, I'm going to give a shout out to Ivan Neo. Ivan streams on Sundays at 7, I think, 7, 8 o'clock, something like that. Okay, I'm going to type it in here. Ivan Neil. Let me see if that works. There he is. Science and Technology. That's him. Yeah, he streams on he was streaming Wednesdays and I think it was or Thursday and Sunday or something like that, and he cut it back to this Sunday for scheduling reasons, and I guess. But yeah, he streams philosophy and rationality, and he is professionally trained in physics, so he understands a lot of that stuff too. So everybody check out Ivan Neal, because he's got a pretty cool stream. If you want to talk about science and rationality and Bayesian inference, things like that. So, all right, so we're talking about magnetics, magnets, because magnets are cool. Now, the question comes up, if you have a magnet, the B word, Bayesian, yes, B word. Yeah, Bayesian. Now, if you have a magnet, you want to know which end of that magnet is north or south. Well, there are a couple ways you can do it, right? If you have a compass, like I had, where do you have my compass, right? If I have a compass and I have a magnet here. This magnet is, I think it's a ceramic magnet, and it's polarized so that one side is north and one side is south. I don't know which is north and south on this magnet. So I want to figure out which is north and south. I take a compass like this, and I just bring it close to this compass, and it'll tell me, right? Can you see that? Let me make this big again here. Give me a second. So I got a compass. I bring this magnet close to the compass, and it'll tell me. It says, okay, that's the north side, and that's the south side. And actually, this compass is backwards. It's set up so that it indicates, because you're supposed to mount it on a boat, and it'll tell you which way you're going. But anyway, so you can take a compass to figure out. But suppose you don't have a compass. All you got is the magnet, and you want to figure out which way is north and south. How do you do that? Well, you have another magnet that you know which is north and south on, right? That we're all on this big planet. That's a big magnet, and we can use that to figure out which is north and south. So there's, if you wanted to figure out, like I took a little, I have that here. Yeah, I don't know what that is. Oh, here it is. I had this little magnet here, which I took out of a motor, of a drone. The motor fried, and so I took this little thing out, and it's got a magnet in it. And I took a nail, and I stuck it to this thing, and I stuck a string on it, and I just hung it from something, and it would this spin until it was pointing towards the north. So let's do that with this one here. We'll take this magnet here. Let me get a thread here, and what I'll do is I'll wrap a thread around this little donut here, and I'll hang it from up on the ceiling there, and we'll just watch it spin, and it should orient itself towards the north or south or whatever, whichever. So let me get some thread here, and we'll do that. Also the B field. Ivan typed into chat. He said also the B field. When you type that in, I'm thinking magnetics. And when I first saw B, I thought, oh, you're talking about the B field. Was it the B field and the M field? I think, right? Isn't that the two? I forget what they are. But that's what I thought when you typed it in there, and I thought, oh, he's going to start talking about real stuff that I don't know. All right, here we go. All right, let me cut this here. Yeah, Ivan, I'm not going to get into a lot of the. I was going to get do the equations and all that stuff, but Tiny Toxic Tofu is kind of doing that right now on her stream this last couple of weeks. So I'm just referring everybody to her stream, her VODs or whatever to learn about that. I mean, I'll get into a little bit of it when I'm building the electromagnet, like the lines of force and the right-hand rule and stuff like that. But all the details I won't get into. All right, so what I'm doing is I'm tying this string. There we go. All right, to this magnet, right? And so I'll hang it on that. I think that's firm enough that I can do it. And I'll do what I'll do is I'll put this. Here's a paper towel roll. I think this will work. What I'll do is I'll fold this up and tuck it through the magnet so it'll actually stick out of the magnet. I haven't tried this. I probably should have tested this before I did this, but it should work. I think it'll work. And I'll tuck this through here, and then I'll hang it up there. And it'll take a while, and I'll do something else while it's trying to figure out which way north is. All right, there we go. So there we go. So now I have a compass, right? But I don't know which is north and which is south. I'll hang it up over here. Let's see here. Not. I gotta put a knot in here. Oops, oh shit. Oh, but it did. It attached all kinds of stuff to it. Okay. All right, so we'll just, can you see that there? All right, so while that thing's spinning around, it should figure out which is north and south all on its own. But it'll just take a while, and it'll go back and forth. It'll twist one way, and there'll be a tension on the, on the torque of the thread that'll make it go one way or the other. Oh shit! It's already finding it. Look at that. It's already figuring out which is north and south. Oh my God. Okay. So when it's all done, we'll know which is north and which is south on that magnet. That's pretty cool, isn't it? But what we're going to do is we're going to make an electromagnet like this. And this was when I first got the idea. I went through and tried to find stuff. I couldn't find just pure iron. That's what you want to use, is just regular iron. Most stuff, like most fasteners, bolts and nuts and nails and everything else, is steel. And depending upon how they formulated the steel, it might have a lot of iron, or it might not have a lot at all. And the amount of magnet, how much it will magnetize, will vary. And you can just take a coil. Let's see, what did I do with that little coil? This right here is called an inductor. Whenever electricity flows through a wire, it creates a magnetic field around the wire. And it does what they call the right-hand rule. I should have looked this up beforehand because I'm doing it from memory now. But if you look at the way conventional current goes, conventional current is the positive carriers, charge carriers, because that's just the way they do conventional current. It's not the electrons. It's conventional current flows from plus to minus, which would be right. Electrons would flow towards the plus, right? Because electrons are minus. Electrons are minus. Protons are plus. And unlike, just like magnetism, the unlike charges attract each other and like charges repel each other. So an electron, being a minus, is going to want to go towards the plus of a voltage. So, but current, when they talk about current in electronics and everything like that, just by convention, they always say it flows from positive down to negative. And you know, when they draw little circuit diagrams and stuff, they'll go like this. Let me bring this up again. Let's see here. Right, there we go. So when they draw little circuit diagrams, they'll draw it like this. They'll say, okay, oh Jesus, why is this not working here? There we go. All right. So let's say that's plus, and this circuit goes through something, a resistor, let's say, and then it goes down here, and this would be minus. And just by convention, when they talk about flow of current in a circuit, they say it flows this way. It flows from positive to negative. But the electrons are actually moving, drifting from the minus to the plus, because electrons are minus. Little electrons are little minus, right? And they will flow this way. But that's not the current, they say, goes this way. So that, anyway, that's just so when we're talking about electronic circuits and stuff like that, conventional current flows to the minus, from positive to negative. So the right-hand rule, I'm pretty sure if I'm remembering correctly, you take your right hand and you say, okay, conventional current is flowing through this wire, meaning that the plus is over here, the minus is over here. Let me bring this back up again here so you can see this. So you got a wire. Let's say this is the plus end over here. This is the minus end over here. So conventional current is flowing this way. You take your right hand, the thumb pointing in the direction of conventional current. Then the lines of magnetic force will curl this way. Will be this way around the wire. And meaning this way, meaning it's going from south to north. Okay, so God, I hope I'm remembering this correctly. We'll find out later on when I actually build the thing. So that means that this is north, right? There's a magnetic field that's going north this way. Now the thing that happens is that when you coil up the wire like this, if you imagine this, it's the field is going this way, right? It's coiling this way north, but then on the other side over here, it's doing the same thing. It's north, right? And it just keeps repeating itself, and each of these coils kind of add on to each other, so that the whole force is going from south through this little coil and north out this way. Does that make sense? So it's like magnifies it. You know, just a single wire will make the magnetic force, but when you put it into a coil like this, it adds up. Each one of these coils, you know, adds up, and the more coils you have, the more it will add up that force. And it's a field, you know. It makes a field, and then the field creates a force when there's something that can act on. And then they found out that if you take something like an piece of iron, this is steel, but let's pretend it's iron, and you put that inside the coil, not only will it make the space around the coil create a field, but that field of that coil will influence the domains inside the metal core that you have on here. And so all the little electron spins inside here will orient themselves too to that field. And that has a multiplying effect, a really big effect on the strength of the magnet. So whenever they make an electric magnet, they won't make it just with coil like this. They'll put a core in it that will greatly magnify that force, the strength of the magnet. I don't know if that makes sense or not, but did that? Okay, so that thing oriented. That's pretty much north. That's pretty cool. So it is pointing north. I can, because I know where north is here. The sun is setting right now. This is the sun. The sun is pointing, is right up that way right now, and it's heading this way. So the sun is set, will be setting over there. Can you see this? Yeah, you can see this. So the sun is over is this way. I don't know if you can hear me or not. Is that way, and it's setting. So that's west. That's east. That's south. That's north. So it's pointing north. So this is the north end of the magnet. So we figured it out. So that's pretty cool. So this is north. This is the north side of the magnet because that's the part that was pointing to the north. Maybe I should label that so I know that. So I have to do that again. So I'll label this magnet as north. This side is north, so I'll know. And there you go. So if you ever have a magnet, I probably don't want to get that close to my tablet there. If you ever have a magnet and you want to figure out which end is north and which is south, that's you can hang it from a string. You can put it in on something that's floating inside of a bowl of water. It doesn't really, as long as there's not a lot of friction, as long as it's just free, so it can turn on its own. And you can figure out which is north and south. All right. So that's pretty cool. And I think what we'll do is I'll wire up a electromagnet. Maybe we could do that right now. In fact, I can just wire up that little coil of wire and see which way it wants to, which way it orients, and we can figure out if my right hand rule was right or not. If I remembered that correctly. Sounds about right. Okay. All right, good. So Ivan says that I'm remembering the right hand rule correctly. So hopefully I'm right. We'll see. We'll see. All right, let's see here. All right, so all right. I think what I'm going to do, I've got a power supply here. This power supply right here, I described at the beginning. It's an old model train power supply that I've heavily modified here so I can get more amps out of it, and it's DC instead of AC and blah 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 with this stuff. And I think what I'll do is I'll take this little coil of wire and this is a power resistor. It's 5 ohms, and I think what I'll do is I'll just wire it through this, and I should get about an amp through this thing, I'm guessing. And we'll wire it up, and we'll figure out if that right hand rule works or not. I'll take a magnet. I guess we could just do it with this thing, maybe with this with that. Or I'll see which magnet, which way is north and south on it, and we'll see if I got that right hand rule right or not. All right, so let me turn this thing on here. Actually, let me do it this way. I don't want to, because even though this is like 12, this is only, 5 volts or 12 volts or whatever, because I'm running it through an inductor like this is called an inductor. Any coil like that is an inductor. It can greatly amplify the current and the voltage through the thing. So I don't want to be touching it when it's actually live. In fact, there's a cap right there. Let me make sure that's shorted out. I just did that. I shorted it out. So we should be okay. We can get a pair of pliers here and we'll just build this thing really quick. Alright. See, what I'll do is I'll put this forward. Can you see that? Okay, we'll just do it right here like that. Alright. I think you can see that. Yeah, that's pretty clear. Alright, so what I'll do is I'll just wire this thing up. We'll figure out which is plus and minus and do that. I'm not gonna solder anything today. That'd be big. I don't have enough room here, and it'd just be kind of complicated to try to get that going here. And dangerous right here in this card table here. That's not very good connection, but I think it'll work. All right, so let's say from the resistor is the positive. Let's say, and then we'll run it through until it goes to the negative. See that? There we go. Did I get that? No. There we go. All right. So very simple circuit here. We're just running it. This is the whole circuit, right? We got plus going in through the resistor. God, I don't think that's a wire around resistor. That would kind of complicate things, wouldn't it? And then running it through our little inductor here, which I built by wrapping this wire around my finger, and then to the minus back to the power supply. And I think we'll get about 1 amp out of it. I'm not even going to bother measuring it. But then we'll see if it actually has a, if it actually turns, makes a magnet turn. Let me grab my magnets here. I'm gonna do is I'm gonna take these magnets. This is a pretty powerful magnet, and I'm just gonna snap it onto this thread so it can be free floating, and then when I apply current through that coil, we'll see if this actually spins or not. There we go. Oh boy. All right, there we go. Does that work? Yeah, it's close enough, huh? I got that chip missing out of that one, so it's off balance a little bit. All right, so there we go. So this end is north, this end is south. Let me adjust that focus a little bit. That wasn't focused just a second ago, wasn't it? It's kind of weird. Okay, that's in focus. I don't know why that didn't. Oh, that's a lot better. Okay, there we go. All right. So hopefully this thing will orient itself to this when I plug it in here. Let me turn this on. So right now it doesn't seem to be wanting to orient either way, really. Or maybe it is. Oh, I got other magnets here. Let me get these out of the way. I got this magnet over here. I don't think I've got any other magnets here. Plus I got the power supply, that's doing stuff too. Okay, well we should be able to see a difference when I turn it on. Alright, here we go. Oh, there we go. So I'll crank up the... Okay, I turned on the power. I think I've got power through here. Yeah, that resistor's warming up, so let's see if this is... Oh yeah, that's... Does that want to get a... Oh yeah, see that? Oh, whoops, let me do it on this side. There, see it definitely has a preference, right? And it's actually pulling towards it. So we don't have a core or anything, it's just wire, just electricity running through a wire. So this is the north. This is north. It's being attracted to this, so this has got to be the south pole of this thing. This has got to be the north pole of the thing, right? All right, so let me shut that off. So we figured that out. Now let me see if that right-hand rule made sense or not. So what I said was that the flow of conventional current, which is flowing this way, from positive to negative, and I said that so this is the, did I do that right? This was south and this, oh shit, this was north. Yeah, it pulled this way. So this is the south and this was the north. Did I do that right? I'm not seeing any flames yet. Yeah, not yet. Not yet. I think there might be. There will definitely be sparks, because when I hook up the bell or buzzer or whatever, there's going to be a contact, and it's fair. You know, you got an inductor making repeated contact and stuff. So there'll be sparks and stuff like that later on. So this is the south end. This is the north end. So let's see if that makes sense. All right, let me just try to imagine this now. So we've got current running this way, and I said it would run the right-hand rule, right? The current running this way, and it would be north. Fingers would be pointing to the north, and they do. See, so it does make sense. See how it would be curving this way, so it points to the north. So that made sense. This is the north end, and this is the south end. So we were right. The right-hand rule worked. All right. All right. So let me put these out of the way somewhere. So we did our first circuit, and it worked. All right. So now what I'm going to do? Let me bring this back up here again. Yeah, that's right. Okay. I was going to do something. Yeah, okay. Let me draw the circuit diagram that we're going to use for the. Let me do that. Let me draw the circuit diagram that we're going to use for this circuit that I'm going to build here. What I'm going to do is I'm going to put a core in here. All right. Let's see. New. Uh-oh. What's this doing here? Save it. No. No, don't want to save it. Okay, there we go. All right, so let me do a quick circuit here. Let me think this through now. All right, so we've got a power supply. We've got plus over here and minus plus. Okay, coming from our power supply. And over here we've got an electromagnet. Let's run it this way. Coils here. And we also have a the spring steel that I'm using, right? That'll be attached on this end. And it'll come up like this. And it'll have a little hammer on the end of it. And then we'll have a bell here that I'll stick on a screw or something, or a bolt or whatever. And so there'll be a core in here with this electromagnet. We'll have some iron or steel or something in here to make that magnet stronger. And so what we want the circuit to do is whenever I turn the magnet on, we want this hammer to come down and hit the bell. But we also want that movement of that hammer to shut off the magnet, so this spring steel will spring back up and then make contact again and go through the whole thing again. And the way we do that is what I will do is I'll run a little wire. I'll have a little contact up here, say, and a contact here. And I'll just run this up to here, up to plus, maybe through a resistor. And then the other end of this magnet, I'll run up to this contact. So you see what's going to happen here is this is going to, when this hammer is up, it'll make contact here. I'll turn on this power supply. It'll normally be up here making contact. It'll energize this magnet. This magnet will pull down this piece of steel, this piece of spring steel, which should be attracted to a magnet. And when it gets pulled down, it'll hit the bell and ring the bell, but it'll also break this circuit here. And when it breaks the circuit, then this electromagnet won't be a magnet anymore. And so this steel will spring back up and make contact again, and it'll just keep repeating several times per second. And if everything goes right, we'll end up with a bell ringing. So that's the plan. That's what we're going to try to do. I don't know if it's going to work or not, but that's what we're going to try to do. And I'm building this. This is just scrap stuff that I've just found laying around in my basement around here and stuff like that. So it's not even, just basic stuff. So I did have, you know what? I'm going to leave that. We got to do this. Let me turn this back down again here so you can see what's going on. What I'm going to do is after I decided to make this, and after I did some tests and stuff, then I decided to go online and read about it, and I learned some things. One of the things I learned that is the equation for a magnet is such that there's a lot of things. Most of it is the geometry of these coils, and also the permeability of the core. So obviously, this thing is not going to be as strong as this thing, even though it's a smaller diameter and all that kind of stuff. This is stronger because it's got a core that's got a lot of iron in it, so it will be stronger. This one just has air in it, which doesn't have as much permeability as an iron core would. But another thing that I found out was that on the top of the equation for figuring out how much force is in there's N, which is the number of turns. So you want a lot of turns, but there's also A for the area of the core. So if the core is bigger and wider and you have a lot of turns, then it will have more force. But on the other side, on the bottom of the there's a fraction, and on the denominator of that equation is L for length of this thing. So the longer the thing is, the less, given if everything else stays equal, the longer this thing is, the less force it will have. And I didn't know that when I first started testing this thing. I just built this. So now what I want to do is I want to take, hang on just a second. So I went through and I tried to find all different things, you know, that might work as a core. And I thought this one would probably be pretty good. I had this thing here that I thought would be really cool to wrap this up maybe and use this, but that's I think this will work the best. And I tested this and it does work as a core. It's actually steel, it's not iron, but I couldn't find anything that was just pure iron that would work. I didn't get that magnet out of there. It's causing all this stuff to... Oh my goodness. Alright. This little guy's causing trouble. Alright, let me stick him over there. Alright. So I think I'm going to go with this because it's shorter, it's a larger diameter, and I'll just, you know, put as many, I'll wrap this thing around this as much as I can, as many layers as I can. And I think that'll work. What I have to watch out for is, because this is a bolt and it's got a very sharp edge, these threads are very sharp here, so I'm going to have to be very careful that I don't scratch the enamel off of this wire, because otherwise then it will short. Real quick story. When I was really young, let me check out chat here really quick. Let me read chat. Let's see. Oh, sounds right. Okay, I'm not seeing any flames yet. Okay. Ivan Neo says, I have to go in a few minutes. Oh, I'm glad I was able to catch some of your stream. Oh yeah, sure, Ivan. Thank you for stopping by. I really appreciate it. Yeah, the way this works, I'm doing this live, so it's going to be kind of tedious. It's not something that's really fun to watch, unless there's a lot of people that can talk and chat and all that kind of stuff. But what I would suggest is to, after I'm done with this thing, is to find the VOD and then be able to fast forward through all the mistakes and everything like that. And you can see the finished product or see whatever parts of it that you want to see. So thank you for stopping by. I really appreciate it. Okay, so let me get back to this now. So this is what I'm going to try to use. I think it'll work, and I just have to make sure that I don't scratch the enamel off of this when I'm wrapping this on there. And I think that will work okay. And what I'll do is I have a board here that I can mount everything on. I don't know what this is from. Old shelving, or I don't know what the heck it's from. I found it on the side of the road. Somebody was giving it away for free, so I grabbed it. So what I'll do is I'll take this spring steel here. We got another magnet here that's getting in the way. So I have this spring steel here, and I think what I'll do is I'll mount it, with a screw like that, and I'll bend it up like this, so it's up here like this, and then I'll wrap the wire around this thing, stick that in there, and that will be my magnet. It'll pull this down, and then I'll use this as and I've already you can see it's already got carbon on there. I was testing it to see if it was conductive or anything that would work for that. And so we'll put something that this can contact on top. So it'll pull this thing down like that. And when it pulls down, it'll disconnect, and when it comes back up again, this will make contact, and that'll be our bell then. And in this thing here, I'll dump all these out, and we'll stick it like this as a bell. See? That's the plan. I think it'll work, but we'll find out if it does or not. All right, so I guess the first thing is to wrap this thing up. And it's not polarized, right? It doesn't matter which is north and south on this thing, because I'm not, this is not a magnet that it's being attracted to, right? It's not, this is just a piece of steel. So it doesn't matter if it's north or south on the top of our little magnet. And either way, I can just reverse the polarity of the power supply if I wanted to do it that way. All right, so let me leave a little bit of space here, because what I want to do now is wrap this around this as many times as I can. And we'll leave this one out here to come up here and have some sort of contact for that thing when it's going back and forth on top of that. Does that make sense? So let's try this now. Actually, let me do it this way. Doing this right here. Do it this way. Yeah, I want to wrap it with the threads. I don't want to go against the threads when I'm trying to wrap it. Hopefully it's not too thick. This wire is actually kind of thick for what I'm doing. I really should have thinner wire, but this is all I got. So what we're going to end up doing is having a magnet that uses a lot of current, because this is virtually no resistance in this thing. It's like 0.16 ohms per kilometer or something like that, or it's some ridiculous amount. So there isn't going to be hardly any resistance on this wire, which means that I need to put in a current limiting resistor in there. We could wire it straight on there just to see what happens, I guess, for a second or two. Okay, I'm going against the thread again. How did I end up doing that? All right, it doesn't matter, I guess, as long as I don't cut into that wire. What do I do here? All right, let's start over here. A little bit more space here. I also went on YouTube to see what they had, what people were doing, and really didn't learn anything new. They had some different ideas on how to do a bell. Some of them would take just a motor, a regular old electric motor, and tie a a hammer to the motor, so that the motor would just spin around and hit the bell repeatedly, and that was their bell, which I thought was kind of funny. But there's another thing that you can do with these magnets. I should probably explain. You can make them into like a horseshoe magnet. You can actually make an electromagnet that's kind of like a horseshoe magnet, and it doesn't have to actually be bent. The core doesn't have to actually be bent into a horseshoe magnet. You can just like I could take two of these things. I could wire up two of these like this, and put a plate on the bottom so that the magnetic flux would flow through both of them, and so one of them would be plus and one of them would be minus, and it would actually make a much stronger magnet. But I'm not going to do that. I don't think it's going to be necessary to do that. All right, I actually want to leave a little bit of space on the bottom to mount this thing on, so let me just stop right there. This is kind of boring. So yeah, if you're on the VOD, just go ahead and fast forward. There's something exciting happening right here, right now. So I should get quite a few turns on this thing, even though it's a larger diameter than the other one. There's also one of the parameters is how close the coil is to the core. So as the coils get further and further away, you know, each layer coil is going to be a little bit less than the one before, but that's okay. And that's one of the reasons why they use enamel on these wires instead of like a regular insulation, like on a wire like this, you know, wire that has insulation like this, is that extra gap makes it so that you get fewer turns of the wire. And they actually on some specialized applications where they really need a lot of strength, they will make the wire square. They'll have square wire so that every inch of the thing is conducting. There's no space at all in between it, which is really cool. And I also found a video online where they were talking about the strongest magnet in the world. And that thing was just, they built it with flat discs to conduct the electricity through flat discs, and they had holes in them in the discs to pump water through it to keep the magnet cool, and it was pretty cool. The whole thing was kind of neat. All right, so there we go. There we got something here. All right, so there's my little magnet. I guess we can test this out to see if this actually is a magnet, right? Just make sure I didn't make a mistake here before I go any further. Oh boy. I'm gonna turn on the light here so I can see what I'm doing. Sun's starting to go down. That's good enough. All right. Make sure my cap is. I'm sure you're not positive and negative here to make sure my cap doesn't have anything in it. The capacitor on the power supply, so I don't shock myself. That's why I did that. I'll hook this up. All right. All right, so we'll energize that thing, and I'll see if it runs. If it actually is a magnet. So I'll plug this in, and plug it in the power supply. Power supply is on. Get the resistor warming up. And let me see if that's a magnet now. A little bit, not much. Well, it's not too strong. It's a little bit. All right, so what I'm going to do is I'm going to take that resistor out, put a smaller resistor in there. This resistor here is 5 amps, or I'm sorry, 5 ohms. So I'm going to take that out because we're probably only getting, let's see how much current we're getting through this right now. Let me, this is this guy, right? It says 300, but this is 30, right? Because I used a different shunt on the thing. This is a shunt. These meters, you know, unless they have a shunt built into them, you got to have, for measuring current, you got to have a shunt that the most of the current goes through. And it's actually what these things do is they measure a voltage drop, millivolts or microvolts sometimes, across a short piece of metal that is a very low resistance. All right, I think I can just get it in here. All right. I'm going to do this kind of a kludge way, but I'm just doing it just to measure, see how much, where we're at on the current. This is kind of a kludge, but that's okay. There we go. All right, and the other end is here. Whoops. All right. I hope I didn't break that. All right. All right, that's good enough, I guess, isn't it? All right, so this is with a 5 ohm resistor, and I don't know how many volts this is putting out, but we'll figure out how many amps is going through it here real quick. Okay, well there's the problem, isn't it? I'm not getting any current at all. Oh, I got that hooked up backwards. Yeah, that was kind of stupid. Glad I didn't break that. That would have been bad. All right, so this time we'll put the positive on the positive side of the meter. We'll put the negative on the negative side of the meter. And hopefully that'll work a little bit better. This is not working too well, but that's okay. Alright, so we got plus coming in here, going across the shunt. Meter should measure, and it goes through that. Okay, let's see. And hopefully we don't get too much back kick from this thing, from that. Alright, there we go. And then crank that up. Okay, there we go. Alright, so I'm cranking this up to I don't know how many volts, and I'm getting 2 amps. And 2 amps is giving me not very much. So I don't know why that is not. 2 amps should be given a lot more than that. So maybe this core is not good enough. Maybe there's not enough iron inside this thing to kind of a problem. Maybe I should go back to the other one. Let me substitute this one back for that one again, and see if I get anything different. See if I get more magnetic force from my original one that I was just testing with. This is a different. It's a smaller diameter core, same length wire, so it probably has more turns, but it's a smaller area and a longer length, so it should have less. By the formula, if the cores are the same material, but this might have a different permeability on this core, which is why it might give it a little bit better, more force on it. All right. That resistor is really hot. That's let's see, what did I say? 2.5 amps, and this thing puts out about 17 volts, but at 2.5 amps, it's probably putting out about 15 volts. So yeah, that's about what, 30-40 watts, and this resistor is rated for 25 watts, probably with a heat sink, so that's probably why it's so hot. I'm going to measure that really quick before I turn it back on. Alright, got a little thing here I can measure how many. So yeah, 60 C. So let that thing cool down a little bit. It's off right now, so that's it. So I just have to wait for that to cool down. I should probably put a heat sink on it or something. All right, we can test it. That should be able to go up to a couple hundred C. So I'll just turn this on really quick just to test this. Now I should get the same thing. Should get about 2 amps through it. But hopefully we'll get more, more magnetic force out of the thing. All right. So power supply's on, and it's probably about 5 volts right now. So let me turn this up. We'll turn this up until we get a couple amps here. All right, that's 1.5 amps, so it's fewer amps. Well, it's a little bit stronger. I think it's a little bit stronger. Huh. Let me try this thing. This is the thing that I'm actually going to be. Yeah, that's not. It's enough, I think. Let's see where this guy's at here. Yeah, 120 C. So that thing's getting pretty hot. I should have that in the heat sink, really, but that's okay. 124. I removed the power to it. Okay, it's gone down a little bit. 96. So that probably won't work long term, having that thing in. But I thought I had actually stronger, a stronger pull on that thing. Maybe I was trying a different, I've got another way I can do this. Here, I can try this. These are some other power resistors, and a long time ago for some other project I needed a very low resistance and a high current capacity, and I ended up putting all these are 1.8 ohm each. I bought a whole lot of them surplus on eBay once, really cheap, and a whole box of them. So I put these all together, and they work out to like 0.1 ohm or something. I forget what it was, but maybe that's a better way to do this on this thing. Is just hook that in there to drop that current. I mean, the big problem here is that I've got this, the only magnet wire I have, unless I scavenge it from somewhere else, is this really thick wire here. That's the problem. If I had a number 24 wire or something like that, American wire gauge 24, then it would be much smaller, and I would have a much longer length in the coil, and I'd end up with a couple ohms in the thing, 5 or 10 ohms or whatever, and then I wouldn't have to worry about that too much current, But let me try this with this other set of resistors. I bet this will work better. Not too out of touch yet. All right, and now put that somewhere where it can cool down. And I'll take this one. I think I'm going to clip these off here so I don't have these big long wires here. Don't clip too much off, but strip these. This is old. Look at this, where the insulation's coming off of this. I don't know what this is. This is some kind of wire for, I don't know, it's really thick. I mean, it's really high, it's probably rated at 20 or 30 amps or something, so it's a pretty good wire, but it's old, so I don't know if it's still. Maybe I should use a stripper for this, but I'm just using my wire clipper. Because that's what I do. There we go. Did I clip too many of the strands there? I don't think so. Alright. Alright, we'll do this one, do the same thing. Maybe a little bit better this time. Alright. There we go. Alright, so those are really, this is a really heavy duty resistor pack here, so this should, I could just hook it up directly, I guess, but this wire here probably is too small to handle a lot of current, This will probably handle a couple amps, and that power supply is only going to put out about 5 amps anyway, I think. Even when it's shorted out, so this wrong. I don't want to put that straight through. I don't run it through these resistors. God, I'm a couple hours in already. Yeah, this is just feasibility here. You know, if I wanted to build something that I wanted to keep, you know, as an actual project, you know, and make it and use it and keep it, you know, this would I'd use terminal connectors and, you know, for everything, and you know, make it really nice. But I just want to just to see if I can do this. I'm pretty sure I can do it, but. All right, let me make sure we got this right here. So now what I've got here is I've got plus. Can you see that? Okay. We got plus coming in here from the power supply, going through this resistor pack, coming back out, going through the shunt, across the meter, going through my little electromagnet over there, and then minus back to the thing. So that should work, right? And I think that's right. All right, so let's turn it on and see what happens. Sure don't have anything here that's going to short out. Okay, here we go. I'm going to apply power. Oop. Power supply's on. Any current there. So let's see. Touch that because it. Let's crank it up. Oh man, look at that! So I just cranked this thing up just to turn it on at 5 volts. There's 5 volts, and I've already got 5 amps going through it. Look at that. Okay, wow. All right, so I didn't know that little power supply would even put out that much current. Okay, so this is going to be a high current thing. You have a lot of current. And these this resistor pack over here, just a few seconds I already feel it's kind of warm. So let's see what happens here. All right, so turn it on. We'll get it up to 5 amps. Okay, now that is really sticky. That's very strong. Oh, you can see that. Can you see how that's really sticking on there good? So that's just 5 amps. I can crank that up to 8 or 9. So that's really strong. Okay, so that's what we'll do. And actually, I think we'll go back to that other one, to this one, and we'll just put more power through it. I don't know about heat dissipation through that thing, but most of the heat's over here on this resistor pack, which this one's up to 65. So this is handling the heat a little bit better, that resistor pack. So I think that's what we'll use. I mean, if I was designing this from an actual design, I'd say, okay, let's use smaller gauge wire. This is 18 or 17 gauge or something like that. And actually, in this size wire, I looked it up. In this kind of configuration, where it's tightly wound like that, it's only supposed to handle a couple amps. In a cabinet wiring, this free wiring, this 17 gauge can handle 10 amps. And when you put it into a coil like that, it's like half or a third or something like that. So we're pumping that a little bit higher than what it should be too. But this is just an experiment. Let me put this one back in there and see if I can get that, because I think this would be easier. This, having a shorter magnet here, will actually be better for that that spring steel thing, right? Because I'm not going to have that much room, right? This is going to be mounted, and this is going to be up here, and you know, so I think a shorter one would be nicer anyway. So disconnect that and put that one in there. And I don't have to worry about draining off that capacitor because right, because it's all I got to do is shut the power supply off, and there's enough. No, it drains off almost immediately when I shut off the power supply. All right, put that in there. And we will have sparks flying, I guarantee you. There will be sparks at some point when the bell is running. We should have sparks flying from the contacts of the bell, of the little contacts of the switch. Let's switch this thing because it's an inductor, and we're current. There's a couple amps here, and so we should be seeing sparks once this thing gets going, which would be pretty cool. All right. All right, so we're going to try this again. All right, same deal. Oh shit, this lost my keyboard. We're still going? Yeah, we're still going. All right, get my tools out of the way. All right, so I've got plus coming in over here, going through my resistor pack, which is still warm, into here through the meter and the shunt meter, and then through the electromagnet and back to minus. So let's plug this in. All right. If we plugged it in, that should be off, all right. So we'll give it, all right, there's 5 amps. And that's sticking pretty good. Way up. So now we're getting less current here. So it's that's interesting. So this thing is, there's some parasitic loss here. Is that hot? Let's see. My resistors are at about 60. This thing is less than 30. So, but there is some loss there. I wonder what that's all about. It's actually keeping the current. You know, it's keeping the current from going on this thing. That other one had higher current, which it doesn't matter. But that's certainly strong enough. That should attract this thing, which is what we want. Okay. So when this thing turns on, it should go like this, and then this part will hit the bell. All right, I think this will work. All right, let me wire it up. Do a little construction work here now. Check my resistors. They're 90. 90C. All right, so they got to cool down. All right, we don't need this amp meter anymore because I don't think we're We're not going to go over 10 amps or anything like that. It shouldn't be much of a problem there. I could probably just wire this in directly, actually, but that, I don't know. I don't think I want to do that. That power supply is way over. I mean, it's rated at, or you know, from the factory. Let me see if it's. Can you see this? Can you see what it says there? Yeah, you can't see it, but it's only rated at like 1.4 amps or 1.8 amps or something like that. And also this guy over here, this right here, this bridge, the full-wave bridge, it's basically 4 diodes all hooked together. That thing's getting really hot too. See, that's at about 80 C. And it's rated at 8 amps with a heat sink. I don't have a heat sink on it, so I got to make sure I don't run it too hot anyway, just because of that guy. All right, so all right, we don't need this meter anymore. Let me get that out of the way. All right, no more. And we want to figure out how to mount this on here so that all this stuff all fits, right? So I want to put that there. I want to bend this up. And like that, right? And put the bell over here somewhere. So let me bend this right at the end here. Bend it up a little bit. I hope this stuff bends without breaking. Should. Oh no! All right, now I got to drill a hole in it. All right, so it doesn't bend without breaking, not very much. But if I heated it up, I could probably bend it. I'm wearing glasses, so I think I'm okay there. All right, that'll work, I guess. It's going to go in there. Get a little bit lower. So I'm going to have to drill a hole in this, which I didn't want to do, because I don't like drilling metal without having it on a real nice steady vise. Alright, so that'll be, I could put like a spacer in there or something. Make that a little bit higher. I'll drill a hole to put this guy in. And mount that way. And then we'll have to bend this to make this hit the bell. Alright, that'll work, huh? I think. And then we'll take this screw here to put the bell on. I think that'll work. Alright, let me start drilling stuff here. It's kind of unfortunate that came undone there. Alright, let me get my drill and we'll start drilling holes here. see what. I think I just want to use just a regular, like a wood screw or something on this. I have one here. I'm going to use a nail. Not sure what would that work? See, it's not going to hold very well on that wood. Huh. I could go all the way through the wood, go all the way through the piece of wood. Do it that way. That might work. Yeah, that would work. I'll go all the way through. That'll give me a nice little terminal here that I can attach the wire to. Is that thick enough? Yeah. I'll just do that. I think that's a number 6 nut. Let me see if I got another nut for that. Let me just use that. Yeah, that's a number 6. That'll work. All right, so I'm going to drill all the way through this. I'll drill all the way through this, and we'll put this on through the bottom of the thing and attach that. That's what we're going to do. All right, so let me find a drill bit that's the right size. I think this is pretty close. I'm gonna also well, I'll just leave that. That's okay. All right. So what I'm doing here, I got my drill, and I'm gonna drill a hole in that piece of wood and drill a hole in that piece of metal and use this little screw to attach it there. So let's see if this is going to go. All right, I've got glasses on, so I should probably use safety glasses for this. Okay, my extension cord. I think that extension cord should handle this drill. I hope. All right. This is not a precision thing here at all. Here, you want to see what I'm doing? Whoops. Can you see that? Yeah, okay. And one more thing. I'm going to kill the mic because this is going to be, I don't want to mess it. Okay, so I'm cutting the mic and I'm going to drill this hole. I'm going to drill this thing. Okay. Okay. My Mac back on? Yeah. All right. I'm going to see if this fits through here. I'm just going to make a mess, but that's okay. I think that's going to fit through there. Should probably countersink that. I'll do that in a second. And then I drill this, same size, and that should work. All right. Now this thing, I'm gonna clamp it a couple times because that can be dangerous to drill metal like this. Is very sharp, you know. If that bit gets caught in there, see this? I don't know if you can see that. I don't know if you can see that, but that's a 50-year-old scar, and I still remember what happened. My dad had to drill some piece of metal or something. He said, "Here, hold this piece of metal while I drill it." Yeah, right. Almost took off my finger. So, yeah. So I'm kind of careful about that. So I'm gonna put this in here. I'm gonna put 2 of these on here. I could get just an actual. I think this will work though. In fact, let me take that. I want to make sure I do this right. So I'm gonna take that guy out. There's my freaking keyboard again. So I'm taking that out. Do I need to take that one out? No, maybe not. No. All right, we'll just do it that way. Okay, so I've got 2 of those guys in there now, and that should be enough. And we'll just drill that puppy. I hope this bit will work through metal. That's steel. That's spring steel, so that's pretty. Going to be kind of tough to drill a hole through, but that's okay. We'll try it. See what happens here. Kind of going through. Oh, I forgot to kill the mic. Sorry about that, guys. I'm going to cut the mic here. That bit that I was trying to drill that with is really not set up for metal. It's set up for wood. Plus, that's really hard steel that it's trying to go through. So I'm going to see if I can find another bit that might work a little bit better. I don't know if this one will work either. I think this one is really dull. I had one that was really it wouldn't even drill through wood. It was so dull. I hope this isn't the same one. All right, let me cut the mic here. So lower the volume. Okay, yeah, I don't have the right bit to drill through that spring steel there. That's the problem. Got it part way through. I bet if I just took like a hammer, a nail, or something like that, I could probably hit it and open that up enough to get that attached. Let's see here. Try to find another bit. All right, I'm gonna try one more bit here. If this doesn't work, then I'll go see if I can find something to punch that open with. All right. All right. Let me cut the mic. Bring it down so it doesn't. Oh yeah, this is working better. right, success. A little larger hole than I wanted to make, but that's okay. It'll work. All right, so we got it. We got a hole in there, and it's a larger hole than I wanted, but it'll still work. All right, so get back to this guy. And actually, that bit, I didn't even think about that. That was the right size for this, to countersink this thing. Yeah, I'm gonna do that right now. I'm gonna countersink this thing, just so it's not, so I can lay that flat once I get it all put together. A bit more. Sorry, I forgot to turn off the mic. Sorry. Sorry about that. All right, there we go. So that's, see, that's nice and flush now, see. Okay. All right, so we got that. Now that guy will go right on there, and we're in business. I think we'll be able to get this thing figured out. All right. Let me check chat here. No, okay, yeah, there was a chat message there, but it was from the bot, so we're okay. All right, and I should use like a lock washer on here, but let me see if I got a lock washer that's that size. That's a little too big. That's okay. There's a washer, a lock washer. I'll do it this way. It'll be easier. All right. All right. So now this guy is going to go under here. I could probably just use, that's probably strong enough that I could just stick that in there. Right? I think so. And then this bell here. Find just 1 second here. I'm gonna go find something to put all this stuff in so I can play with this bell here. All right. Set that over here. All right, so this bell will stick over here somewhere. And this ought to be the right height for that, I think. All right, like that. Oh, here. See, like that. And then we'll have this little guy under here somewhere. That'll be pulling that down to hit the bell. There we go. I think I'm going to wire this up right now just to see how this magnet does on that. Just using that steel. See how much permeability, I guess, this spring steel has in it. It's going to be conductive. I wonder what that will do. Alright, so I'll turn on that magnet and just see if it... Turn on the... run some current through that thing just to see what it does. Oh, there we go. It worked. So just that. Can you see that okay? I don't know if you can see that. But all I do is turn that on and it pulls right up and on it there. Yeah. All right, so that'll work. That has enough. That's attracted the magnets good enough. I guess I could have just done it with a magnet, right? Same thing. Okay, so now what I'll do is I'll drill a little hole for this guy and put it in there, and then we'll figure out where to put the bell. I think that'll work. All right, so I'm gonna find a drill bit that's about the size of that, and stick it in there, right about there, and like that. Bet you thought that was a screwdriver, didn't you? That's actually... All right, let me find a drill bit that's this size. Okay, this is actually a little smaller. This bit is actually a little smaller than that. It's almost about that size. But, and I think, well, I'll have to glue it in there. I didn't want to do that, but that's okay. So I'll drill that right about there. And actually, I'll do it at an angle, so that'll be... I don't want to have to bend this thing anymore. So I'll just put that in there at an angle, maybe. Oh no, wait, that won't work because I've got those coils there. I guess I'll have to figure out how to bend this a little bit. Yeah, I'll do it at a little bit of an angle. Alright, so we're putting this bit in here. This is a big bit. It's about the same size as this bolt. Pretty close. And so I'm going to drill just a very shallow little hole here for this little bolt to go underneath this spring steel here. So we'll see if that works. And I'll do it at a little bit of an angle. Alright, so before I do this, I'm going to turn down the mic again. Because I know how irritating it is to have somebody run equipment like that with the mic on. So, alright, mic's going off for a little bit, or down. Okay, I drilled a little hole in there. A big hole. Not too deep. And what I'm going to do, I have another bolt that's exactly the same as this one. And I'm going to use that to kind of get threads going in there a little bit in that wood. And maybe I can do this so that it doesn't, so that I don't have to actually glue it. I can just twist it in there. Yeah, see, this is going to work. Look at that. It's going to make its own thread, almost like a wood screw. It's a bolt, but it's... Alright, that's good enough. And I'll put that other one in there. Hopefully that... So you see what I'm doing here? I'm just basically just screwing it right into the wood there because I don't want to glue it. And that should be enough to hold it. That worked out really well. That's in there pretty good, actually. All right. So twist this guy back over. All right. So now I'll test it again. Okay. This is taking a little longer than I thought. I thought I'd be done in 3 hours. Well, it's not even 3 hours. I started at 2, I guess, so it's not too long here. All right, I just want to test this real quick here. You ready? Here we go. Forgot to hook up the positive here. Let me short this out. And hook up the positive. I shorted out that cap. See, I turned it on and then I unplugged it, but that positive wire, this is important. You guys should know this if you don't know this already. I forgot to hook up the positive wire, the positive lead from the power supply. I turned on the power supply and nothing happened. And I looked and I said, oh, the positive isn't hooked up. So I unplugged the power supply. But before I touched that wire, I touched that positive wire to the minus wire of the power supply to short out that capacitor so I wouldn't shock myself. And because I'm using an inductor in this circuit, it gets kind of dangerous, you know, unless you take precautions like that. So that's what I did. All right, so I think it's all hooked up now. All right, we'll try it again here. Ready? Big test. Let's see if the electromagnet's going to be able to pull that striker down. Here we go. Oh, it tried. Did you see that? All right, let me turn it up. No. All right. So I guess it's not close enough, huh? What's going on there? So let's bend this down just a little bit here. So it's even closer to it. what I'm trying to do here is I'm trying to adjust this spring steel so that it will strike the top of that electromagnet flat. There we go. See what I'm doing here? So that should work this time. And maybe I wasn't making a good enough connection here either on these wires. I'm just kind of very temporarily putting them on there. Maybe I gotta get my current meter hooked up again. Alright, so I'll try this again. Can you see that? Alright. Alright, so I'm going to plug it in and hopefully it'll make that thing go down. There we go. Alright. It's working. You can probably hear that too, huh? So my little electromagnet is working. When I give it power, it's pulling down this thing here. Now all I have to do is put the bell here. In fact, what I think what we'll do now is I'll turn this into a buzzer just to see if it'll work as a buzzer. So what I want to do now is hook. I guess I'll make this thing positive. No, I should make that negative, shouldn't I? Doesn't matter, I guess. Yeah, that should be negative, I guess. It could be like the ground of the system, I guess. Alright, so what I'll do is I will connect. Put my other glasses back on so I can see what I'm doing. I'll hook up this other there's a couple more washers here so I can get a good connection on that. So what I'm going to do is I'm going to hook up minus from the power supply to this thing. Then this thing will actually act as a switch. And I'll put a contact up here and it'll just like that. And hopefully that'll work and make a lot of sparks, which is always exciting. You see what I'm doing? I'm hooking the minus. This is the minus from the power supply. I'm hooking up to this spring steel thing here. Oops. I thought I was hooking it up. Alright, let me try harder. Maybe I should have stripped that a little bit further. That's okay. All right. So Yeah, I can run it just like that, actually. I'm just going to use, for right now, I'm just going to use this copper wire as a contact on here, just to see if it works. All right. So this is just like the schematic that I drew at the beginning, earlier in the stream, kind of. So what we got is we got this wire here, which is making contact here. So we got minus coming from the, or let's go plus, right? Plus goes through the resistors into the coil, this side of the coil. The other side of the coil comes out, touches this top of this spring steel. Electricity continues to flow into the minus back into the power supply. When that happens, it'll energize the coil. It'll pull this thing down, which will disconnect that little wire there. I don't know if you can see that or not. You can see that, right? See that? See that wire is just, it's making contact there. So, all right, anyway, that should work. But if I'm doing this right, it should make a little buzzer sound and make lots of sparks. Should probably get that sawdust out of the way when I do that too. That's sounds like a recipe for disaster there. All right, I'm gonna put my goggles on because it might make a lot of sparks. I don't know what it's gonna do. Okay, I think that's going to work. All right, ready? We're going to test the buzzer. Here it goes. Didn't work. I saw sparks. There it goes. Hear it? Oh, I was doing it just for a second there. It was buzzing there for a second. Let's see here. I may need to now I may need to put this contact on like a spring-loaded thing or something, so that the contacts actually spring. Oh, that might work. All right, let me try it again. There we go. Hear it? Let me shut the light off. You can see the spark a little bit better. Whoops. It doesn't run that long. So it's buzzing. You can hear it buzzing, right? Let me put my headphones on here if I can hear it. It's just a little buzzer. Now, I don't know if that's enough of a stroke to ring that bell. Alright, so we got a buzzer anyway. And sparks, some sparks. Probably a lot of ozone too. I'm going to try to hook this thing back up here. What I should do is put like a plate of metal that would attract more of that, but I don't know. We'll just, I don't know, that'll probably work, huh? Huh. Yeah, I think what I'm going to do I think what I'll do is take a nail, pound a nail in, attach this to the nail, this lead to the nail, and bend the nail over so that it's touching, and maybe put this thing in there. And I should probably have like a spring of some sort on there. You know what I mean? So that it's actually has a little bit, is energized longer before it goes down there. Let me put this in here. Let's see what that does. I'd like to see that move a little bit more. Might have to put a capacitor in here or something to keep that energized a little bit longer. Put this over here. Alright, disconnect the power again. Why don't you put this over here and see what that does. What this should do is give me a longer stroke before that disconnects, you know what I mean? And I might have to put, you know, another screw or something right here that will provide more ferrous material for that magnet to pull down. All right, let me just try that and see what that does. Oops. Well, it's making a nice sound. There we go. Just needed more current. Okay, it welded itself the contact welded to the thing. Oh my god. Alright. Let me just go back to here, go back to plan B, plan A, C, whatever I'm on. Alright, so let's see what that does. Oh, that sounds better. Oh, look at that. So the problem here is that this is, when it's sparking like that, it's actually welding the tip of the copper wire to the thing. It's getting stuck on there. All right, let me try that deal with a nail here. See if I can get that. I'll try just first I'll try just doing it so it's just right onto this guy, right? Put that nail in there and then bend it over. All right, let me do that real quick. Let me make sure this, before I go through all that trouble, let me make sure my nail is conductive. Duh. I'm sure it is. I mean, it's right. But we'll check it out here anyway. All right. Okay. Alright, so I'm going to put that in there and then bend it over a little bit. This table is not too firm, but I think I can do it right here. Alright, we're going to turn down the mic. Whoops. I don't know if I'm going to even be able to bend it with this pliers. I should have thought about that. Huh? Yeah, nails are always bending when you don't want them to, right? So it should be easy. That's pretty close. All right, so you're just going to bend it just a little bit more. All right. Let's see what that looks like. You know what I could do? I could flip that around maybe or something. I don't know. I don't know. Be real careful. I don't want this thing to snap on me. Well, I think that'll work pretty good. Let me try that. See, when things don't go right, just grab a hammer. You can fix anything. Oh, hammers always fix everything. All right, let's see. All right, and then we'll wind this guy around this. All right, so that's pretty tight there. That's on there. It's on there. That's on there. Okay, so microphone back up so I can explain what's going on here. All right, so we've got Let's go from positive to negative, right? It's got positive coming in here from the power supply. It goes here, right? Connects here, goes through my resistor pack, connects to one lead of the solenoid of the electromagnet, goes through the coil, energizes the magnet. The other end comes up here, goes through the nail. Nail goes to the end of this little bolt here, the screw. Completes the circuit and goes back to minus to the power supply, and it works. And it energizes this magnet, the electromagnet. Then, when the electromagnet gets power, it sucks down like this. And I don't know if you can see that. This contact here will break, and it should go back and forth like that if everything goes well, and hopefully it doesn't short out too badly. I mean, I don't want it to weld that nail to the to the end of that screw. I don't think it will. All right, here we go. Ready? All right, what did I do wrong here? I just need to adjust it a little bit better. Oh, I know what I'm doing wrong here. All right. All right, this is not connected tight enough to that thing. That screw there, is not was not connected tight enough to the to this, so it was just wobbling around. So I gotta screw that in a little bit better. Unfortunately, this is a slotted screw. It's a really old bolt here, slotted head bolt on here. So tighten it in really good. Okay. I think that'll work. I also have this, I don't know, I'll just try it too. See if I get it. Okay, here we go. Maybe I should solder that stuff on there. It's just not making good contacts. Anywhere. All of them. Let's see here. It just needs a little bit of tweaking here to get this thing. I pretty much have it here. I think one of the problems is that I should have some more mass here, more iron mass here. This is spring steel. It probably doesn't have a lot of iron in this thing, so that would help, I think. Having some more iron on there. Okay, look at chat, and have a chatter. Big Ducky Snow. Hi, Stephen. How are you? Stephen is a friend of the channel, and he says, hello, my Debbie buddy. I'm just getting into a Pilates workout, so I hope you'll be live in an hour. If not, then at least I got to come and hang with you all for a little bit. I shall be lurking and wishing you a great rest of your stream and day. Well, thank you, Stephen. Thank you for the good wishes. How was it? Just a minute ago. So thank you for coming to the stream and checking this out. I'm building a buzzer and maybe a bell if I can get it to work. So that's what we're doing here. It's being a little temperamental here. See, I had the bell here. Let's see if that's going to be enough to ring that bell. Let me see if this even... Yeah, that makes a bell sound. Okay. All right, let's see if we can get that to make a bell sound. I don't want to hang on to this. This has a current going through it, so I don't want to hold this. I don't know. I'll hold it with this thing. There we go. All right, we got it. There we go. Good bit. All right, so I think we can get there from here. This is going to take a little bit of trial and error. Oh, I see I passed my 3-hour limit here. So maybe I should continue this on another stream. I think I'll do that. Something smelling like it's cooking here. Let's see, that's at 60. My nail's getting hot too. Touch that and it's hot. Yeah, I think I'll continue this on another stream because it's getting kind of cold in here too. We've dropped a couple degrees here. But I think I got it. I think I have a path to get there from here. Okay, time to sweat, rock and roll, and see you later. Okay, Big Ducky Snow, thank you. Oh, let's see, Big Ducky Snow, it says, also, I've been doing pretty awesome today. Our Dyson is kaput. Dyson, Not sure what a Dyson is, but we found some pretty good alternatives on Amazon. The reviews are good, as are the prices, and replacement parts are easy to find and afford. Dyson, maybe a Dyson vacuum, maybe. All right, so I think I can get this going here. I just need to tweak it a little bit, and I think I need to have a, like a piece of metal or something there. To give more ferrous, material, more something that will attract the magnet better. But I think we got it. We got a little bit of a bell going there. All right, we'll continue this on another stream here. But that was fun doing that anyway. So I think we got it figured out. We got a path to success there. Maybe I'll read a little bit more. See if there are any other tips on how to do that. I think there's maybe that contact needs to be a spring on it, so it's making contact for a longer period. You know what I mean? Energizing it more, and maybe make it so it has a little bit more throw on the, that stroke has a little bit more, goes a little bit further. Although I think it's pretty good the way it is actually. All right, so I'll do that. We'll pick this up on another stream. I appreciate everybody stopping by. Who stopped by? We had a couple visitors today. Oh, let me do a shout out to Big Ducky Snow, because he's a friend of the stream here, and he stopped by. Big Ducky Snow. I think I spelled that right. Did it work? Yes, it worked. Found it. Join us in following Big Ducky Snow. Yeah, he does work streams. He does Pomo streams, where he work. It's a system to help people concentrate on their work, and you work for so many minutes, and you take a break for so many minutes, and do that over and over. And do it on stream so you can have multiple, your buddies doing it with you to encourage each other and all that kind of stuff. So he does that. He does karaoke singing. There's a karaoke singing on stream, and he also plays a car racing game, which I can't remember the name right now, but it's a car racing game. He has a wheel and everything that he does this driving. So everybody check out Big Ducky Snow's stream. All right, so we'll continue this on another day, and maybe I'll stream, play with it a little bit, get some ideas, and we'll finish it up on another stream, and then we'll have this thing ringing this bell. That'll be fun, huh? All right, everybody, thanks for coming, and I'm gonna wrap it up here. All right, take care, everybody. Bye.